Welcome to this explainer. Today we're exploring an absolutely foundational concept in modern software architecture. When we think about data systems, it's incredibly easy to picture just a single monolithic database sitting right at the center of an application, quietly holding all of our information. But the reality is, as applications scale, that simple picture completely shatters. A monolithic database eventually becomes a massive bottleneck. You start running into severe resource contention, where heavy analytical read queries lock up tables and literally starve out the critical real-time write operations your application actually needs to function. Because of this, data in modern architecture has to live a really fascinating double life. It's not just about reliably storing day-to-day transactional information anymore. It's also about crunching massive volumes of historical data to figure out how a business is actually performing. So today, we're going to unpack exactly how that works by deeply exploring the trade-offs in data systems architecture, specifically zeroing in on data warehousing, systems of record, and derived data.
Okay, let's dive into this and start with a somewhat provocative question. Does your database actually know if it's operational or analytical? This question gets right to the heart of a fundamental divide in data architecture. The way data is accessed largely dictates exactly how we need to structure and store it. Now, originally, databases handled all sorts of data altogether: social media posts, multiplayer game states, financial ledgers, you name it. The basic access pattern historically just looked like processing a standard, isolated business transaction. But over time, the people querying the database split into two entirely distinct camps. You have the software interacting directly with the end user, and then you have the business analysts trying to understand that end user.
To truly understand these two camps, let's draw a sharp contrast here. On the operational side, we have online transaction processing, or OLTP. This is the absolute lifeblood of your web or mobile app. It relies heavily on point queries, usually leaning on B trees and heavy indexing to look up a very small number of records using a specific key for millisecond-level latency. It's constantly handling day-to-day transactions, inserting, updating, or deleting individual records based on immediate user actions. But on the analytical side, we have online analytical processing, or OLAP, and this is a totally different beast. Instead of fetching one user's profile, an analytical query might scan over literally millions of records to calculate aggregate statistics. This requires completely different storage optimization. Instead of row-based indexing, OLAP often relies on scanning massive volumes of data using column-oriented storage to minimize disk I/O. Just imagine a business analyst at a supermarket chain. They aren't looking up a single receipt, right? They want to know the total revenue of each store or which brand of baby food is bought alongside diapers across a 3-year period. These are massive, arbitrary, ad hoc queries designed purely for business intelligence. Now, back in the day, people actually used the exact same databases for both of these workloads. SQL is highly flexible after all, but there is a massive inherent risk here. Think about it. If a business analyst runs a monster aggregation query without perfect index support, it triggers a full table scan. That scan trashes the buffer cache, exhausts the CPU, and literally starves the operational database of the resources it needs to process live transactions. The result? Your customer-facing checkout page times out and crashes. Not good. Because of this architectural nightmare, in the late 1980s and early 1990s, a major trend emerged. Companies just stopped using their OLTP systems for analytics altogether. They realized they needed to create a dedicated, safe space for their analysts. And that safe space is the data warehouse. Essentially, a data warehouse is a separate, read-only database that analysts can query to their heart's content without ever risking those live OLTP operations. Picture a large modern enterprise. They might have dozens of independent operational systems running at once. There's one system for the customer-facing website, another controlling the point-of-sale checkout in physical stores, another tracking global inventory, another optimizing delivery routes, and a completely different one for employee HR. A data warehouse provides a unified environment optimized specifically for extracting all of that fragmented, siloed data and bringing it together into one cohesive place for business intelligence. And this workflow brilliantly illustrates exactly how that unification happens. If you follow the flow of data from the very top, you've got your active users, a customer, a warehouse worker, and a truck driver. They're out there interacting with those operational systems we just talked about: the e-commerce site, the stock keeping app, the route planner. Each of those applications relies on its own dedicated, fast operational database. But as the data flows down, we see a distinct separation. Data is being securely pulled from those independent operational silos down into a single centralized data warehouse at the bottom, where our business analyst is sitting,
ready to safely run their heavy analytical aggregations. So, how does this actually build into a formal pipeline? Well, getting data from those operational silos into the warehouse follows a very specific set of steps known as ETL. Step 1 is extract. You take a copy of the data from your OLTB databases or even extract it from external SaaS products like a CRM using specialist API connectors. Step 2 is transform. Operational data is usually highly normalized or kind of messy, making it really hard to analyze at a glance. So it gets cleaned up, joined together, and transformed into an analysis-friendly schema. Step 3 is load. The transformed data is finally written into the data warehouse. Actually, quick architectural side note here, sometimes the order of those last two steps is swapped, which gives you ELT. With the rise of incredibly powerful, scalable cloud data warehouses, it's often way more efficient to just load the raw data first and then use the sheer compute power of the warehouse itself to run all those transformations natively. So, data warehouses are fantastic. Business analysts absolutely love them because they use a relational data model queried through standard SQL, which is just perfect for BI reports and dashboards. But the narrative doesn't stop there. As analytical workloads have become more demanding, systems have had to become even more specialized. Enter the data scientists. Data scientists aren't just looking for historical reports, right? They're looking for novel insights. They're out there building complex machine learning models, creating recommendation engines, and doing predictive analytics. And for these cutting-edge tasks, the rigid, highly structured relational rows of a standard data warehouse just aren't always the best fit. Which brings us to the data lake. If a data warehouse is a highly organized, highly structured filing cabinet, a data lake is exactly what it sounds like, a massive pool of raw data. It's a centralized repository holding copies of data in its absolute raw, original file format, without imposing any upfront schema whatsoever. While a data warehouse stores rows and columns, a data lake happily holds text documents, images, audio files, sparse matrices, and application logs, usually leaning on cheaper, commoditized cloud object storage, making it incredibly flexible. Though to be fair, as any data engineer will quickly warn you, without proper governance, a data lake can very, very quickly turn into a murky data swamp. There is a fantastic quote from the source text that perfectly captures the philosophy behind the data lake, the sushi principle. Raw data is better. Why exactly would raw data be better? Well, because data scientists rely heavily on a process called feature engineering. They need to transform data into dense vectors or matrices of numerical values to train a neural network or use natural language processing on raw text reviews to extract granular sentiment. If that data has already been heavily scrubbed, joined, and forced into a rigid SQL data warehouse schema, valuable granular nuance is often completely destroyed in the process. Giving data scientists direct access to the raw, untransformed data allows them to shape it exactly how they need it for their specific, complex mathematical algorithms.
Okay, let's pause for a second. We've talked about operational databases, data warehouses, ETL pipelines, and data lakes. Now I want to completely shift our perspective. Let's zoom out from these specific database technologies for a moment and look at the underlying conceptual flow of data across an entire organization's architecture. Because whether you are interacting with a relational database, a search index, or a cutting-edge AI model, data fundamentally flows in a specific direction. And understanding this flow, that's the real key to designing robust, scalable systems. This flow, it always begins at the system of record, also known as the source of truth. This is the database that holds the authoritative, canonical version of your data. When new data comes into your application, for instance, when a user updates their profile picture or successfully completes a payment, it is first written right here. The data here is typically highly normalized, meaning each fact is represented exactly once to strictly avoid any inconsistencies. Think about your own system's absolute baseline truth. If there is ever a discrepancy between a cache, a search engine, and this database, the system of record is, by definition, always right. The counterpart to the system of record is derived data. Data in a derived system is the result of taking existing data from another system, like your system of record, and processing or transforming it somehow. Now, technically speaking, derived data is completely 100% redundant. It just duplicates existing information. To a junior developer, this might seem totally counterintuitive, like why duplicate all this data? But here's the magic. If a server catches fire and you lose your derived data, you don't panic because you can entirely recreate it from the original source of truth. The whole reason we bother duplicating it is that it's an essential architectural trade-off to get incredible performance on read queries. You derive different data sets from a single source so you can view that exact same data from different highly optimized technological angles. So the crucial point is that you are probably interacting with derived data systems all the time without even realizing it. Let's ground this theory in reality for a second.
A cache? That's derived data. If it's wiped out, you just fall back to the main database to recreate it. Search indexes are derived data. They literally reorganize the system of records so users can search by keyword efficiently. Materialized views, which pre-compute common read operations, derived. And here is the big one. Data warehouses and trained machine learning models are derived data systems. Analytical systems are ultimately just massive, highly specialized consumers of redundant data that was officially created somewhere else. Bringing this whole shebang together, we can confidently view the modern data ecosystem as a continuous, unidirectional journey. Data originates as single, atomic facts, securely written into operational systems of record through those low-latency point queries. From there, it flows outward. Through processes like change data capture or complex ETL pipelines, it's duplicated, transformed, and pushed into specialized, read-optimized derived data destinations. It flows into caches for millisecond user-facing reads, into search indexes for keyword queries, into data warehouses for massive business intelligence aggregations, and into data lakes for raw machine learning analysis. Every single tool has a specific architectural job, and the clarity of your infrastructure depends entirely on knowing which data is your definitive source of truth and which data is merely a derived view. Which brings us to our final thought for this explainer. I want you to look closely at your own applications and infrastructure. Are you genuinely optimizing your data for the right read and write patterns? Or are you accidentally mixing your systems of record with your derived data? Are you trying to force your operational database to run heavy analytical aggregations, or dangerously treating a volatile cache as a source of truth? Recognizing the dual life of data and cleanly separating your operational sources from your derived analytical views is the absolute master key to building systems that are both highly reliable and massively scalable. Thanks for joining me on this deep dive, and I hope this gives you a powerful new lens through which to view your own data architecture.